It is section 30.2, basis, functions, and Taylor series. Let's begin with an observation. In the history of the engineering research and development, there have been two major mathematical techniques, the change of variables and representation by basis functions. The change of variables is a basic technique used to simplify problems, and a function can be either represented or approximated by a linear combination of basis functions. That's the reason the basis function method have been so popular in engineering R&D. Okay, let's see this example. Find the solutions of the systems of equations. We have two equations, two nonlinear equations of two variables x, y with these conditions. X, y are positive and y is larger than x. For this problem, by introducing a change of variables, you can get the solution much more easily. Here, we'll try to use these change of variables. S is xy and t is x plus y. Okay. Then here also, because this portion can be written as now xy and x plus y, so that we can simplify these terms by using this change of variables. Okay, the first equation can be changed into xy is s and 2x plus 2y is twice of t, which is 20. From second equation, that is now s times t, st equal 48. Okay, we have resulting equations much simpler than original one. From the first one, we have, for example, s equal 20 minus 2t. By using this one, from the second equation, we have s is 20 minus 2t, and now t equal 48. Now, we can solve this problem quite easily. It's quadratic in t, so it's quite easy. Okay. We'll move these terms to right side and expand and try to divide by 2. Then that same is t squared. Okay, there's minus 10t and plus 24 equal 0. So that we have 4 and 6 separation, minus minus, which means that t is 4 or 6. T is 4 or 6. In this case, the corresponding s must be, now once t is 4, then s must be 12. And once t is 6, then there must be 8. So for s and t, we have two pairs of values. Okay. So that is a first pair and there is a second pair. And with the first pair, now s is 12, so that, okay, t is 4. So here, t is x plus y, which is 4, and s is xy, and that is now 12. That is one part, and the second part is now, and that is t is 6, which means x plus y equals 6, and s is 8, so xy equal 8. if you're using the same technique, for example, move y to the other side and plug 4 minus y here, and that'll be quadratic equation for y, and you can get possibly two solutions for y, and then you can get the corresponding x values. So there are possibly two solutions from here, two solutions from here, but you can get them by using the same technique quite easily. So there are total four solutions, but among them, here x, y both must be positive, and y must be larger than x. So you can find the unique solution, which will be here 2 and 4. So among four solutions, that one is satisfying these conditions. Okay, you can finish the computation yourself. Most subjects in calculus, particularly in vector calculus, are deeply related to the change of variables. With change of variables, you can handle differentiation and integration over the higher dimensions more effectively. So you have to understand the change of variables quite deeply. Okay. Here we define bases. A basis for vector space V is a set of vectors or a set of functions that is linearly independent, and that spans the vector space V. Here, linearly independent means that they are, once they are producing through linear combination, then one element in the set cannot be made from other entries, so that one cannot be made from other entries means that they are really independent, because the production is along with linear combination, and we say such independence is linear independence, right? Once the set of vectors or set of functions having such property, then we say that set is linearly independent and span the original vector space means that every vector or function in the space can be made, can be expressed as a linear combination of these basis functions. Then we say that here the basis is spanning the vector space. Let's see example. You can understand it more thoroughly through this example. The monomial basis for polynomial space Pn. Okay, this space is the collection of all polynomials of degree n or less than n. And for the polynomial space Pn, we can consider a monomial basis 1x, x squared, and xn. And along with these functions, the polynomial, any polynomial in Pn can be expressed here 1 times C0, C1 times x, C2 times x squared, and we have such linear combination of these basis functions. So that means that here these functions are spanning the polynomial space. And also, you cannot get any entry, any function here, for example, x squared, it cannot be made from other entries. That means that x squared cannot be a linear combination of other terms here. So that means that this set is a linear independent. So this is a linear independent and spans the polynomial space Pn. So this is a basis, but each term is now a monomial term. So that we say that is monomial basis. Okay. Okay. In Rn, we define E1 is the first direction, and the first component is 1, every else is 0. So if you consider in R2 n is 2, then you can make it, you can visualize here. Now 1, 0 is that one, so that is E1 in the x direction. And E2 is the second component is 1, every else is 0. So in R2, that will be E2. Okay. In this way, we can have the unit vector, length 1 vector, and E3 and up to En. So En, the last one is the last component is 1, every else 0. So such collection is called standard unit vectors in Rn, and it becomes the standard basis for Rn. The reason is here for any choice of x in Rn, we can write this way x1 to xn, but it can be written along with this linear combination of E1 to En. So any vector, an arbitrary vector in Rn, can be expressed as a linear combination of these standard unit vectors, so that these standard unit vectors span Rn, and also each of these unit vectors cannot be made from any linear combination of others. For example, E1 cannot be made by using others, because every else over there will be 0, so that any multiple of these vectors cannot become 1 here. So they are linearly independent. So that's the reason the collection of these unit vectors is form a basis, and we call it a standard basis because it is a standard unit vectors. Now for the given vector space, you can formulate other bases. And this is the standard basis for R2. But for R2, again, you can make some other bases. So for example, one vector is the same as E1, but another vector, okay, let's try to write down a unit vector. That is 1 over square root of 2, and also the second direction, second value is 1 over square root of 2, like that. So the length is 1. Pictorially, here, one vector is this one, and another one is a 45-degree angle and length 1 vector here. If we say that is u and that is a v, then there is u and there is a v. But these two vectors will form a basis, because every point in plane, you can express this point by using a linear combination of these two vectors. Okay, So here we have two directions basically. To recheck that one, you go and now, okay, go back and parallelly move that way. So that here first move this direction and parallelly move that one. And here a multiple of u, of course the coefficients will be negative, will reach out over there. And a multiple of v, if this is parallel to v, then a multiple of v will make that vector, so that this combination will make that point. That means in this arbitrary point can be expressed as a linear combination of u and v. And also here, biasing one, and you cannot make the other one. And biasing this one, you cannot make that one. So they are linearly independent. So this is a basis for R2. In this way, you can formulate various bases for given space. But we'll deal with this one a little bit more later in chapter 6. Okay, this is end of the part 1, and we'll continue in the second part. Thank you.